Okay, so now we're going to analyze a log function. So let's take this function here, x squared natural log of x. Okay, and remember this function has domain 0 to infinity because of the natural log. So if we take the derivative of that, we're going to have to use the product rule. So we're going to get x squared times 1 over x plus 2x times natural log of x. I think I may have done one either like this or very similar earlier where I found the derivative. So we're going to get x plus 2x natural log of x, and you can factor an x out of this. And so when you factor an x out of this, remember x, you're going to get x times 1 plus 2 natural log of x. Now x cannot equal 0. Now you can solve just a second. So as I was saying, x can't be 0, but 1 plus 2 natural log of x can be 0, and I solved it here. If you solve that, you can move 1 to the right, and you get 2 natural log of x equals negative 1. Then divide by 2, and you get natural log of x equals negative 1/2. And then just convert this to exponential form, and you get e to the negative 1/2 is x. So that's where I got this value, and x, that's approximately 0.61. Okay, so I'm going to break my number line up. I'm going to start it at 0. Remember, I can't go to 0 or to the left of 0 because of the domain. So I'm going to go 0 to e to the negative 1/2, and then I'm going to go e to the negative 1/2 to infinity. Well, a number less than e to the negative 1/2 is 0.5, and a number greater than e to the negative 1/2 is 1. So if I plug 0.5 into here, you can plug 0.5 in, and you get you're going to get x is going to be positive. But if you plug 0.5 in here, 1 plus 2 times natural log of 0.5 is going to be negative. So you're going to have positive times a negative. So you're actually going to get a negative. So the derivative is negative, so the function is decreasing on that interval. Now if you go to the right, plug 1 in up here, you're going to get a positive here and a positive in here. So the product's going to be positive. So since the derivative is positive, the function is increasing. And since the function is decreasing to the left of e to the negative 1/2 and increasing to the right, then e to the negative 1/2 must be giving you a minimum. So the minimum is actually e to the negative 1/2 and f of e to the negative 1/2, or e to the negative 1/2 and minus 1 over 2e. And again, to get the y value, I plug e to the negative 1/2 into this function to get it. And I went ahead and gave you approximations here in case we want to look at the graph later. Okay, so now the second derivative, if I get the derivative of this function, I'll take x. Let's see, what did I do? Let's see. Oh, I'm sorry, I actually did it from here. So to get the derivative, let me do this again. I got the derivative from here. So I took the derivative of x, which is 1, and then here I had, for the second term, I had to use the product rule. So I treated it as 2x and natural log of x as the two factors. So then I take 2x times the derivative of natural log of x, and that gave me 2x times 1 over x. And then I took natural log of x times the derivative of 2x, and that gave me 2 times natural log of x. And then when I multiplied this together, the x's canceled, so I just got 1 plus 2 here, which is 3. And so I get 3 plus 2 natural log of x. And if you set that equal to 0, you can do it just like I did up here, except this will be a 3. So you'll have a 3 here, then when you move it over, you'll get a negative 3, and then divide by 2, so you get natural log of x is negative 3/2, and then convert it to exponential form, e to the negative 3/2 must equal x. So that's what I got. That's what makes the second derivative 0. And now I got an approximation of that as 0.22. So I just chose to use 0.1 to the left of e to the negative 3/2 and 1 to the right of e to the negative 3/2. Well, when I plug 0.1 into this, I actually got a negative value. So the second derivative is negative, which means the function's concave down on that interval. And then when I plug 1 in, I actually got a positive value for the second derivative, which means that f is concave up on that interval. Well, since the concavity changes, it must change at that point e to the negative 3/2 and its corresponding y value, which is f of e to the negative 3/2. Now again, I took e to the negative 3/2 and I plugged it back into this function up here to get the y value, this weird y value of negative 3 over 2e cubed. Okay, but then I went ahead and gave you approximations so that we can look at it on the graph. Well, if you look at the graph, remember the domain starts at 0 and goes out to infinity. Okay, now we found out a couple things. We know that we're going to get a relative minimum at x equal e to the negative 1/2. So this point right here, even though it's approximately 0.6, it's actually x equal e to the negative 1/2 is the actual x value. So that's the exact answer for that x value. And then the y value you can look up there to see. So there's your relative minimum there. And then this right here, this point right here is where x equals e to the negative 3/2. So that's e to the negative 3/2. And that is actually where the inflection changes. So basically, it's really difficult to see here, but you basically are getting kind of a downward bend from here to here. So you're concave down here, but then from there on out, you've got an upward bend, so you're concave up. And that corresponds with what we had here. We're concave down between 0 and e to the negative 3/2, and we're concave up from e to the negative 3/2 out to infinity. Okay? So anyway, again, you can use this information to actually get the graph, get a rough sketch of the graph without actually having to use a graphing utility. Oh, one thing I didn't talk about was increasing, decreasing. The first derivative told us it was decreasing from 0 to e to the negative 1/2 and then increasing to the other side of e to the negative 1/2. And you can see it's decreasing till you get to here, and then it starts increasing. So see, it all works. And there's another practice problem you can try below with the graph given, if you want to give that one a shot and see if you can get the same answers I got. Now, when we were talking about exponential functions, we talked about y equal e to the x, but what happens if you have a number other than e to the x? What if it's a to the x, like 2 or 3 to the x? Well, let's take the derivative of both, let's take the log of both sides and see what happens here. If we take a log of both sides, we get the natural log of y, and then if we take the log of this, natural log of a to the x, we can actually write that as x times the natural log of a using log properties. Okay, now, and then we can implicitly differentiate this, and when you take the derivative of natural log of y, remember you get 1 over y prime, and the derivative of x times natural log of a. Now, natural log of a is just a constant, so the derivative of a constant times x is just a constant, so I would just get the constant. And then when I solve this, multiply both sides by y, I get y prime equal y times the natural log of a. Okay, but remember what y was? Go back up here. Y is a to the x. So the derivative of a to the x is simply a to the x times natural log of a. And so there you go. Now, if you've got a to the u, you got to throw in the chain rule. So it would be a to the u times natural log of a times the derivative of u with respect to x, or just u prime. Okay? Now, here's an example. So if I want the derivative of 5 to the x, I can use this formula. A is 5, so I would have 5 to the x times the natural log of 5. See, that was easy enough. So that's the derivative for that. But if I have this one, where I have a, which is 3 in this case, but instead of x, I have a function of x, x to the 4th minus x squared, well then I have to use this formula. So let's see what I have for this formula. I've got 3 factors. Always start with the function, so I'm going to have the function a to the u, so I've got that. Then I'm going to multiply by the natural log of the base, and the base here was 3, so multiply by natural log of 3. And then you multiply by the derivative of the exponent with respect to x. So the exponent was x to the fourth minus x squared. So what's the derivative of x to the fourth minus x squared? It's 4x cubed minus 2x. Okay? All right. Now, for logs that are of a different base other than base e, what you can do, you can use the change of base formula. This one's pretty easy. You just use the change of base formula, and you can rewrite this as natural log of x over natural log of a. And then if you take the derivative of this, you're just going to get, this is just a constant, so the derivative of this is going to be the constant times the derivative of natural log of x, which is simply going to be 1 over x times natural log of a. Okay, so in other words, if you have the log of x base a and you want to take the derivative of that with respect to x, then you just do 1 over natural log of a times 1 over x. Now, but if you have the log of some function of x, then you've got to throw in the chain rule. So it'd be 1 over natural log of a times 1 over u times u prime. Let's look at two examples. So if you want the derivative of log of x base 2, you're just dealing with x now, so you can do that just by saying that's going to be 1 over the natural log of 2 times 1 over x, which is 1 over x times the natural log of 2. But if you have the log of a function of x, like 1 minus x squared with a base, well then you do 1 over the natural log of a, which I would get 1 over natural log of 5, and then times 1 over u, so that would be 1 over, I lost my square there, that should be x squared. So 1 over 1 minus x squared, okay? And then you multiply by the derivative of 1 minus x squared. And what's the derivative of 1 minus x squared? It's minus 2x. So that's where the minus 2x came from. That's the u prime, okay? Now, there's a product here. Here's a product of two functions. So basically, you know how to do the product rule. So I take the first function, which is this, and then multiply it by the derivative of the second function. So now the derivative of this would be 1 over natural log of 3 times 1 over 2x plus 3, and then times the derivative of 2x plus 3, which would be 2. And then switch the product rule around, do the other half of the product rule. I would take this function, which I just wrote it right here, and then I would have to get the derivative of 5 to the x squared. Well, the derivative of 5 to the x squared is actually 5 to the x squared times the natural log of 5, and then times the derivative of x squared, which is 2x. And then the rest of it was just trying to simplify it to the best that I could. Okay? Okay, pause the video and then read this in the gray here. And then when you're done reading, restart the video, and I'm going to show you one more example. Okay, now how do you find the derivative of a function of x raised to a function of x? Well, the first thing you want to do here is you want to take the log of both sides. So I'm going to take the natural log of both sides. Then using log properties, I'm going to write the right-hand side as x times the natural log of 1 plus x. Then I'm going to implicitly differentiate. So the derivative of natural log of y, we've done this several times, is 1 over y prime. And this is a product, so I have to use the product rule. So I take x times the derivative of this natural log, which is just going to be 1 over 1 plus x. Then I take the natural log times the derivative of x, which of course is just 1, so I get natural log of 1 plus x. Well, then to get y prime by itself, you can multiply both sides by y. So you get y prime equals y times all of this. And then, guess what? We know what y is, because if you go back up here and look, y is 1 plus x to the x. So we can go back in and replace this y what it equals, and we can actually get the derivative in terms of x. And so that's how you find the derivative of a function of x raised to a function of x. And that pretty much ends that. I think I've got some applications in the next section that I'm going to talk about.